So class, today we are going to discuss about transmission lines. Let's start with a simple question. Can you tell the voltage between these two resistors in this circuit? Yeah, it's quite obvious. It will be V by 2. Answer will be similar in case of AC. Now consider this circuit with the following AC as input. What is the voltage across this first resistor? If you observe properly, it is 0 and not V by 2. So what has changed? Actually, wavelength of input excitation has become very small. So we can see that circuit no more behaves the same way when wavelength of wave becomes comparable to the circuit elements. Assuming resistance to be of 1 centimeter in length, that's equal to wavelength in our case, frequency comes out to be 30 GHz. That's way much more than the normal circuit that run on AC of 50 or 60 Hz. But in EM domain, we work at much higher frequencies and these principles become important. This happens because at high frequencies or very low wavelengths, lumped element model is no longer valid. You all might be knowing what is lumped element abstraction from your ELL100. Still, let me explain it once so that everyone is at same footing. Basically, it makes the simplifying assumption that attributes of the circuit like R, L, C, and G are concentrated into idealized electrical components or lumped elements, joined by a network of perfectly conducting wires. The lumped element model is valid whenever LC is much smaller than lambda, where LC denotes the circuit characteristic length and lambda denotes the circuit's operating voltage. But when lambda smaller than size of PCB or microstrip, we cannot use lumped parameters. Then we need to divide whole circuit into small paths such that the new path length is smaller than lambda and we can use lumped parameter theory in that path. In these scenarios, we use more general models such as distributed element model, which include transmission lines. These models' dynamic behavior are described by Maxwell's equations. So, to send an electric signal, we need two wires. Since two metal conductors placed side by definition constitute a capacitor, this means each section of our transmission line has some capacitance. And since each loop of wire is by definition an inductor, each section of our line has some inductance. Also, as wire has some inherent resistance, each section of our line has some resistance. Similarly, we can say that as insulator between conductors are not perfect insulators, so there is a finite conductivity between these two conductors at each section. So, the lumped element model of section of transmission line looks something like this. A transmission line is basically a cascade of many such small sections of this circuit model. You might be thinking that we added L and C forcefully without any reason, but it is not so. Suppose we applied DC voltage across our transmission line. The capacitance and inductance are what prevents the signal from traveling instantaneously through the transmission line. Therefore, we can never remove this capacitance and inductance completely because this would then violate Einstein's theory of relativity, which states that information can never travel faster than speed of light. So these capacitors and inductors shown are not components that we deliberately added to the circuit, but are inherent part of all wires that carry electric signals. So now coming on to the mathematical treatment of a transmission lines. Consider the following lumped model of section of transmission line. Here values of various lumped elements are given in per unit length basis. For the analysis, we will apply KCL and KVL in this circuit. Using KVL in this loop gives V across these points equals to V drop across resistance, voltage drop across inductor and voltage across these 2 points. Similarly, applying KCL on this node, we have current coming through this branch going to capacitor, conductance and this branch. So we obtain the following two equations. So when we divide both sides by delta z and put limit delta z to 0, the last terms get converted into derivatives. And hence we obtain the following differential equation. Minus r minus L di by dt minus dv by dz is equals to 0 and minus g dot v minus c del v by del t minus del I by del z equals 0. These two equations are also known as telegrapher's equation. So how should we go ahead in solving these equations? Actually, here we can use Fourier transform in time domain to convert derivative VRT time to multiplication by j omega. So class, just do it and tell me what does this result into. Come on class, it's simple mathematics, 11-12 stuff. Yeah, so it comes out to be del V by del Z is equals to minus R plus j omega L into Iz, and di by dz is equals to minus g plus j omega c dot vz. These equations can be solved simultaneously to get Iz and Vz as these. And here gamma is the complex propagation constant given by under root of product of R plus j omega L and G plus j omega C. So solving equation 7 and 8 for Iz and Vz, we get Vz is equals to V naught plus e to the power minus gamma z plus V naught minus e to the power plus gamma z. Similarly, I comes out to be I naught plus e to the power minus gamma z plus I naught minus into e to the power plus gamma z. Here, e to the power minus gamma z accounts for propagation in the positive z direction and e to the power gamma z for the reflection in negative direction. Putting this Vz equation in this equation that we earlier had, we obtain Iz in terms of these parameters of transmission line and V plus and V minus. We can call this factor R plus j omega L divided by gamma is equal to Z naught. This is the characteristic impedance of transmission line. So current can be rewritten as V naught plus e to the power minus gamma z divided by z naught minus V naught minus e to the power gamma z divided by z naught. So now, with the transmission line clearly defined as circuit element, it can now be analyzed when a load is attached. We define the load to be located at z is equals to 0 to simplify the analysis for now. So, using this equation and this one and setting z is equals to 0, we get ZL is equals to Z naught into V naught plus plus V naught minus whole divided by V naught plus minus V naught minus. Rearranging, we can find reflected voltage in terms of known values as V naught minus is equals to ZL minus Z naught divided by ZL plus Z naught whole multiplied by V naught plus. So the ratio of reflected wave to the incident voltage wave, which is also known as the reflection coefficient, is given by V naught minus divided by V naught plus, that is ZL minus Z naught divided by ZL plus Z naught. An important case should be observed from this equation. When the load impedance matches the characteristic impedance of the transmission line, the reflection coefficient becomes 0 and therefore there is no reflected wave. This load is also referred to as being matched to the transmission line. Don't worry if you haven't understood what matched load is. I will start from here in the next class. And just to remind you all, today is the deadline for assignment submission. So that's all for today. Thank you.